Alright, so we managed to get through some basics for C# structures, how we can evaluate the code, how to break it down into individual operations, and how to use a little table to guide us through the step-by-step process for using data, writing data, and so on. And we had a quick look at a few different operations and at a few different data types. And today we're having a closer look at data types, some more types that we haven't discussed last time, and a better look at how they actually work under the hood, because that can be important knowledge. And we're also probably gonna look at some more operations. So first off, some integer data types. Should probably write this out a bit better, since you're supposed to read this and understand. No, that's too far apart. I'm not really sure what style I want to go for here. Yeah, that should be enough. Integer types. So we saw last time the int, which is 32-bit, and we also look at byte with 8-bit, and we also looked at uint, and well, technically sbyte for unsigned integer and signed byte. And we had to make this distinction because the same 32 or 8 bits could be used for positive numbers only, or for positive and negative numbers. And the first thing we're going to do is have a look at how that works. How do we store negative numbers using the same 32 bits or 8 bits or however many bits we have that we usually would use to just represent positive numbers in a binary system. Let's make a simple example with just 3 bits for now. So for example, 1, 1. In binary, this is a 5 in decimal. And let's look at another one, just a simple one. That's a 1 in decimal, 0 in decimal, 7 in decimal, and binary. These are all positive numbers. This would be the basic way to use binary numbers. Just we use the exact same system. We use decimal, just with 2 symbols instead of 10. Right? Base 2. If we look at this on number line, so we have 0 here, for example, 1, 2, 3, 4, 5, whatever. 6 didn't quite work out. 7. This would be 0, 0, 0, 0, 0, 1, dot, 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 dot. 2, 1, 1, 0, 1, 1, 1. Like that. This is now the range of numbers we can cover. Like there are some numbers further up, like 8, and there are some negative numbers on this side, this 1, so on, but the only numbers we can actually use, that doesn't look so good, are in this range. Like just from here to here. To store negative numbers, we could of course just go ahead and move this number line down here a bit to the right. So we could decide that maybe this is our new 0 here. And this is a 1, 2, 3, and this would be -1, -2, -3. It's for example, we still have the same range for our binary numbers on top, but now they represent some positive and some negative values. we still have a total of 8 different numbers. Just move the 0 place a bit to the front, and this would be 1, 0, 0, by the way, in our system. This is now the new 0. 1, 0, 1 is now 1, 2, 3, and on the other hand, 0, 1, 1 is the new -1. Let's add the last one too. 0, 1, 0, like that. And this can be used, of course. Like, there's no reason why we couldn't do it this way, but it's not the most comfortable way to handle it, since, well, let's make a simple example. If we have some logic for unsigned values, for just straight up direct binary representation of our decimal values, this 1 or 5 plus, let's just add 1, 0, 1. Classic binary system, this would be now 1, 1, 1, 0, which is a 6. So works out just fine. Now let's try to use the same with our numbers here. We had a 5 and a 1, we added them together, so 5, well, we can even represent that in this system, so maybe let's try something smaller. Let's just try the 2 plus 1, so 2 plus 1, and the normal binary system, 0, 1, 0, 0, 1, 1, 1, 0, so 2, 1, 3. And with our new system, the 2 would be 1, 1, 0, plus 1, 1, 0, 1. And them together we get 1, 1, 0, 1, 1. So if we use the same logic for addition we used for regular base 2 system, we would get the wrong result. This would be now -2, -1, at least in our current system here. So we can't use the normal logic anymore. And, well, that's still possible. It means we would have to have 2 different pieces of electronic in our CPU, which just wastes space and resources. So ideally, we would find a way to handle this negative number stuff, which could still use the same logic, for example, for addition. That'd be ideal. And one way to solve that is by turning this number line into a circle, because keep in mind, with only 3 digits possible, only 3 bits, well, once we go beyond 7, like adding 1 to this, well, we would be at 1, 0, 0, 0. This would be 8. But we only have these 3 digits, so basically we go back to 0. Modular arithmetic. We have actually a circle, a number circle, not a number line, with a fixed number of entry points. So we might have, let's try to, well, whatever. Try to draw a circle, so 1 there, we had 8 like that, and then quarters, half as well. So on a regular circle would have 1, 2, 3, 4, 5, 6, 7, and we would have 0, 0, 0, 0, 0, 1, and so on until we get to 1, 1, 1. And then if you imagine the 1 in front, we would get back to 8, but we only have the last 3 digits, so we get back to 0. So if we go clockwise, we add, and if we go anti-clockwise, we subtract. This is a small detail we get to later. Now, if we try to do the same thing we did here, with moving the numbers a bit around, Well, just moving the numbers in the circle doesn't really work, but we could imagine that instead of going the whole way around the entire circle and just adding up 1, 1, 1, we can also go anti-clockwise and subtract. So from 0 we go to -1, -2, -3, -4. So we still have basically the same idea as here. We move along the available numbers, matching our bit combinations. It's just the placement, where we place the numbers. So if we look at it, if we just look at these numbers on top, we would get to 0, 1, 2, 3, -4, -3, -2, -1. This would be the new order. If we start at 0, 0, 0 and go to 1, 1, 1, 1, we have this sudden jump from the highest positive to the lowest negative number. And what this does is, if we try to make the same calculation as before, we add 1 to 2, well, both are the positive integer values that we already know, the same as normal binary representation, and using the same logic as for only positive integers, we still get 3. Just normal values. No problem here. But something funny happens when we use the negative values now. Let's, instead of adding a 1 to the 2, let's add a -1. So 0, 1, 0. Let's actually try that in the positive values first. We make the addition of 2 to 7. 1, 1, 1. 2 plus 7. And then we get 1, 0, 1, 0, 1. There's a 1 in front, but we have to ignore that because 3 bits only, and we add up as 1. Which, if you keep in mind, clockwise is plus. If we start here and add 7, that means 1, 2, 3, 4, 5, 6, 7. We make one trip around the circle and end up here at 1, which is the same as adding -1, if we look at it this way. The same bit values and the same position in our circle, which can be used as the same number. It still mathematically works out. 2 plus -1 is equal to 2 minus 1, which is 1. So in fact, going forward, a certain amount of steps can be the same as going backwards, a different amount of steps. So by adding 7 to 2, we have the same result as subtracting 1, at least in this scenario with exactly 3 bits. And so having this 1, 1, 1 share the double duty of representing a 7 and a -1 is perfectly fine. We can still use the same circuits for adding the values, which is great. So we can keep that in line, and that's why this system is used basically for every integer number, at least the signed ones. Let's remove this for now. Let's write the numbers down, because there's a certain detail that should be clear, should be made clear. Let's see, 0, 1, 0, 1, 0. Let's count with me. 3, 4, whatever. 0, 1, 1, 1. So 0, 1, 2, 3, 4, 5, 6, 7, or 0, 1, 2, 3, -4, -3, -2, -1. So these are two options to handle this. We could either use positive only, or we can use positive and negative. And if you have a look in here, we have this split right at this point. And this is exactly the point where this first digit jumps from 0 to 1 at the halfway point. That's why the first digit here, the most significant, the leftmost, if you write the number out, is also the sign bit. And the other numbers are just the value. Because basically now I can look at this number. If it's an unsigned value, well, it's just part of the number. It's just 4 plus whatever is on the right. If it's signed, however, well, this just means this is a negative number. Which is pretty convenient to make certain checks. If you want to check if my number is less than 0, well, you just check the first digit and you immediately know it's a negative number. On the other hand, if you see the first digit, it's not a 1, but a 0, then it's a positive. Did I misspoke earlier? I have to look in the recording. If so, my bad. So, positive, 0, negative, 1. That's why it's called the sign bit. And this is signed because we basically move the numbers a bit around. Circular logic, modular arithmetic, and we can still use the same calculations, but they can either be negative numbers or positive numbers, and they still work out the same way. It's just interpretation. The same numbers go in and come out to the same result, and it's just a matter of how we interpret the numbers, that they suddenly become negative or not. But it doesn't matter for the actual operation, which is the cool part about it, which is why we use it everywhere. Maybe a different way to look at it. There's this really great talk, which I can't remember where I saw that. But basic explanation would be, for this system to work, which you can do in decimal too, by the way. This is not unique to binary. We can do the exact same thing in decimal values too. It's just a bit weirder to see than in binary because you're used to decimal numbers working a different way. But the negative numbers, what are they? They are the inverted version of the positive ones. So whenever you have any number, positive, plus 2, and you add the negative value, the inverted value, you end up at 0. That's the property. You always have the counterpart, the complementary number that would result in a net 0. And so with our modular arithmetic, well, we go for a value like this, and we are now trying to look for another value that would set, when we add it, set everything to 0. Well, to set everything to 0, we just go, basically, take this number, in this case 8, and we subtract this first value, and then we get the actual value that we would need to add to get 3 zeros. And for a 2, 0, 1, 0, that's 1, 1, 0, which would set everything in these 3 digits to 0. So again, that talk made a really, really cool explanation of why that works and the very mathematical background. Look, if I find this, I will try to remember to add the link in the VOD, at least in the upload. So if you look at the VOD, maybe check the description. Hopefully I remembered, and hopefully I found it again. If not, well, too bad. But yeah, that's how we do negative numbers. Oh, maybe a simple way to convert that. This was now relatively easy because we only worked with 3 digits, but as soon as we get a couple more, this might get complicated. So four. Okay, now this is 8-bit. This is a positive number, an 8-bit. What would be the counterpart to that? What is this if we inverted that? Maybe not easy to see immediately. There's a trick to that, and it's called the 2's complement. We just take the same number and invert every single digit first, which just works by switching the digit around. If it's a 0, we go to a 1. If it's a 1, we go to 0. 0, 0. 0, 1. Just negate everything. And then we have to add 1 to this, as if it was just a regular number. Ignore the whole negative, positive whatsoever. And that would then turn this, we add 1, so this is 0, that's 1, 1, 0, 0, 1, 0, 1. And this is the counterpart to this. This is the inverted version of that number. So if we add them up now, so we ignore this, this is just intermediate product, let's just erase it completely. That's 0, that's 0, 1, that's 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, and this is skipped off and we're back at 0. So invert every single digit and then add 1 to that number, and you have the 2's complement, which is the same number just inverted to its negative counterpart, or actually to its positive. We can do the same again. We invert every number, 1, 0, 0, 1, 1, 0, 1, 0, and then we add 1, and it becomes 1, 0, and it's back. So you can do the same continuously to switch between the positive and negative values. So also that means that if you do that on something like 3-digit number 0, well, 1, 1, 1 plus 1, 0, 0, 0. So the inverted value of 0 is just 0. That also means there's a little quirk with signed integers, which you saw earlier. In our 3-bit version, we had positive values, 0, 1, 2, 3. So the 0 is like a positive number, is counted in the positives. But the negatives had the other 4, which is -1, -2, -3, and -4. So on the positive end, we only go up to 3, but on the negative, we go up to -4. So there's a little quirk. The negative values are seemingly larger, or have seemingly larger range than the positive ones. That's just something to look out for. Also, right, the counterpart for, if we use -4, that was 1, 0, 0. If we invert that, well, we end up with 1, 0, 0, 1. So +1, that's 0, 0, 1. And we get back to the same number again. So the inverted version of -4 is -4 because we cannot store the inverted version. There is no 4 in the positives. We only can go up to 3. That means we get an overflow and end up at -4 again. So 0 and the smallest number are both basically immune to the 2's complement because they both end up at themselves again. But yeah, that's signed and unsigned. Integer is the most basic integer type. I mean, it's named after integer, so makes sense. It's the default type that C# uses when you want a whole number. It's assuming you start by integer. If you need something smaller, maybe just 16 bits, well, you can take short, which is literally named because it's just like an int, just shorter, because it has only half as many bits. And the same logic applies then to a number that can be bigger. If you need more space, if you need a longer number, you end up with long, which has 64 bits. And they also come as short, long, and U short, U long, just with a signed, or basically with an unsigned in front, because by default they are signed. And that's integer types. Actually, always start with the basic int, and you can either shorten it to get a smaller number or extend it to get the long number. And byte is a bit special because the other integer types are by default signed, and byte is only 8-bit, and it's named because 8-bit are a byte. That's just the terminology. And by default it's unsigned, and you actually have to get a special version of that to get the signed one, which I honestly never used, by the way. Like something like a U long and rarely uint. I've never used the ushort. I rarely use shorts, by the way. And I've never used sbyte. Not really sure what the purpose is there. Maybe for ultra efficient programming where you really have to cram a lot of data in but don't want to lose convenience. I'm really not sure. Well, whatever. I mean, technically there is another integer type, but that is very special type that we'll get to in another lesson. Then another type you've seen, or we talked about, was bool, which is in the booleans. And actually that's as bool. That's the only one. It has 1 bit. Don't confuse it with the 1-bit number though. Like, these are all numbers. Zero, 1, 2, and potentially -1, -2, and so on. Depending on if it's signed or not. This is just true or false. It can only have these two values, not 0 or 1. If you write a 0 or a 1 in C#, that means you're talking about a number. This is about a true or false value. It has 1 bit. In the computer, that's a 0 or a 1 internally. But as far as the program is concerned, this is not a number. This is either true or false. Just a Boolean statement. There are other number types though. So maybe whole numbers? Whole numbers? Because these are just integer types. Just whole numbers, fixed range. You add 1 to get to the next one. There are other types of numbers, other number systems. Like, for example, these would cover something like natural numbers and maybe natural with negatives. But they are real numbers. That's the entire range we haven't discovered yet. And there's some more complex stuff as well. With complex numbers and whatnot. Before we get to those, let's make a simple program though, because I want to show you something important. And so I'm trying to not mess it up this time, because yes, I messed it up yesterday, which never happened. Yesterday didn't exist. So we're talking about a variable a, which we start at 100, basically the same I did yesterday. And we never did yesterday. Let's ignore yesterday exists. No, yesterday didn't exist. I should stop talking about yesterday. So, like that. And now I say b equals, now I'm doing it the right way, 5 divided by 9 times bracket a minus 32 bracket semicolon. That's our program. Let's try to run this. The same way I explained it last time. First instruction has 2 operations. We have the declaration and we have the assignment. Declaration has priority, so we start by initializing an int a with no value yet. Then comes the assignment, which assigns the value of 100 to a. So now we do have a value in here. Then next instruction, just the declaration for b. Okay, no number yet. Then comes this large instruction. Let's write this out proper way. B equals 5 divided by 9 times brackets a minus 32. And we have a couple of operations, the assignment, division, multiplication, subtraction. And we have brackets here, so regardless of the other operations, this subtraction here has priority. That's the first thing we need to do. And to subtract, we need 2 values. We have a 32, but we still need to figure out what the a is. We look that up, so this is b equals 9 times 100 minus 32. And we can perform the operation now. 100 minus 32 is 68. And now we can drop the brackets. because there is no longer any operation it can support, can give priority to, so this ends up just as 5 divided by 9 times 68. And now we have assignment, division, multiplication. Assignment has the lower priority, but division and multiplication have the same priority, at least in C#. And so we go from left to right. If they have the same priority, our operations start at the left and go to the right. So first we have to divide. Well, we have two numbers already, so we can make the division. And so B equals... Well, what does this actually come to? Well, 5 divided by 9, 5 9, that's 0.55555555, and so on. 5 repeating, I think you call it. But we are working with integer numbers here, whole numbers. Like 0, 1, 2, 3. There is no 0.55555 in the integer world. It doesn't exist. So C# will simply perform this division by ignoring everything that cannot be fully fully explained as a whole number. It's like, let's say 12 divided by 5 is equal. Like, this is something we would write in elementary school sometimes. This is like 2 plus 2 divided by 5. This is the rest of the operation. This is what's left over. And in C#, if we're talking about integers, this is all we left with. This part is just removed, doesn't exist. And if we're talking about 5 divided by 9, well, that's just only the rest. And the value we're left with is 0. The 0.555, everything that would come here, is just completely erased. It doesn't exist anymore. Because we're working with integers explicitly. And so we're left with 0 times 68. Multiplication has priority over assignment, so this is now b equals 0. And now we can assign the value, and we end up with 0. Which is a problem. Because our formula here is giving us instructions to calculate the temperature in Celsius based on the temperature in Fahrenheit. 100 degrees Fahrenheit is not 0 degrees Celsius. And actually, more damning, doesn't matter what we put in here. Even any other temperature in Fahrenheit would always result in 0 degrees Celsius, because we always multiply this value by 0. So what we can do is restructure our program. Instead of making the multiplication in front, do it in the back. So first we take a minus 32 times 5 divided by 9. What is this going to do? Well, let's look at the program. I'm going to speed through it a bit. So we have b equals a minus 32 times 5 divided by 9. And this is then b equals 68 times 5 divided by 9. So just skipping some steps here. We now have the multiplication happening before the division. So we first multiply 68 by 5. So we have 340 divided by 9. And this time when we divide, we don't lose as much as before, sort of. This time we can actually say b equals 37. Technically that would be a 0.7777. Like, this would be more accurate, but we skip this part because we're in the integer world, so we're left with 37. It's not the exact number, but it's way closer than always having 0. Basically, by restructuring the program, we made the error we get by losing the decimal points have less of an effect. We just moved the removal of data further back into the process, so the error is small, the overall error is reduced. That's one way to do it. The other would of course be to simply use different data type. What data type? Well, let's have a quick look at how we can store data. Can only store it as bits. So this combination of ones and zeros is a number. And for integer types, we already know how to handle that. This could be either a positive number or a negative number. Keep in mind, the first one is right now 1. So if this is a signed value, we know this is negative. What else could it represent? Well, what if we said this is a number with decimal spots? So let's say this is where we assign a decimal. We take the whole number, but the last few digits are actually for what's coming after the decimal value smaller than 1. And there are also different ways to handle this. Let's maybe show that in actual decimal values. Base 10 might be easier. 1, 8, 2, like that. 27,182. Let's assume we only have 5 digits space. This number, if we just assume that, hey, there's a decimal point, so we are left with 271.82. Well, assuming we only have 5 digits, we can also do something like this. This is as small as we can go, except of course for 0. But the smallest value smaller than 0 would be 0.01, which is quite small. And we can go up to 999.99. So this is not bad. So if we look at the number line again, so we have 0. And let's say this is 1000. Well, if we put the decimal at the second place here between these digits, then we can represent almost the entire line here. What if we move the decimal further in front? Well, now we have 3 digits for the decimals, but only 2 left for everything in front. So now we massively reduced our range, but we get a way higher density. With the old system, with just 2 digits, well, 0.01 is the smallest value we can represent. That's our resolution, basically. So we had... I'm exaggerating a bit here. Like, it's not that loose. It's far denser than this, but if we compare it then to this other version, it's the same number of total amount of numbers, but more compressed in terms of range. So we get more accuracy, we get more precision, but we lose total range, which numbers we can represent. If we move it even further in front, well, we get even more precision. But we are trapped in terms of range. And we can do the other way around. We move the decimal further back. Well, suddenly we get way higher numbers we can represent, but way less dense, way less accuracy. Exaggeration, of course, again, but no matter what we pick, if we just decide that one specific spot is how we want to place the decimal point, we always have to sacrifice one option. We can either have a lot of big numbers but lose precision, we might as well just go with integer values, or we have only very small range but a lot of precision in that range, which is also not ideal in every case. So usually in programming, for most users, we actually make this variable. So let's clean this up a bit. What if 2718, we used the first 4 digits for a number, and then I had another digit which tells us where we place the decimal point. For example, this could be then 2718 and 81. This could be 271.8 and 27185. Well, that could be point. Bit of a mistake. No, that works. I mixed those two up. That's why it looked so weird. This is why this also looks weird. 2718, like this. So we can actually get big numbers, 4 digits, but we can also get very small numbers, just by moving a decimal point depending on our needs. If we need some small precise values, well, we pick a higher value here, and if we need some smaller values, or some bigger values with less precision, take a smaller value here. And this is the basic idea in scientific notation, where you care about some values, like 2.7182, let's put it like this, 5 digits again, and 10 to the power of, well, for example, 0, if you just want 2.71, or you make it times 10 to the power of 3, and then you get 2.71. Let me write this out properly. 2 point international, don't put a comma, bad habit, 2, and this would be 271.82, but you can also go with negative values, maybe like that, and suddenly we have 2.027182. Scientific notation. This x10 is always the same, is always there, so we can basically ignore it for the number. Decimal point doesn't matter either. We only have the digits themselves, the order in which they are arranged, and we have a number that tells us where in these digits we place the decimal point. Somewhere in here, maybe further to the right, maybe further to the left, and that's how we get a large range of numbers. We can get very precise, or we can get very large. All options open. And because the decimal point isn't fixed anymore, because we didn't put it at digit 1 or digit 2 or at digit 500, we can mix and match depending on our needs. It's called a floating point, because the decimal point can move about. And there we have things like float, which is floating point. You see a trend here. Integer is the default pattern for integers, and for floating point numbers we have something like a float, which is 32 bits, by the way. Some of those bits are dedicated to basically storing the, what we saw earlier, the digits, the shape of the value, so to speak, and some other bits are dedicated to tell us how far those bits have to be moved left or right. Where's the decimal point? Funnily enough, other than with the integer, the float isn't the default value for its category. That would be the double, which is 64 bits. So at least that trend is the same. Double is just like a float, just with double the amount of bits. And this is the default that C# would use for integer types and for decimals. There's also the decimal, which is another data type, which has 128 bits. But decimal type doesn't work exactly the same way as float and double do. It's a bit special, and I basically never use it. Like, apparently it's good for currency. If you're working with finances, maybe then. I mean, I've seen it at work for finances, but that's the only case I've ever seen it used. Like, everything else always floats or doubles, depending on how much precision I need. Or, well, usually I always go for double unless I have memory constraints that I'm worried about. Where I have a lot of numbers that I have to store and process, then I sometimes go for float. And that's some basic types. Let's go back to our example. So we could use a double. Double. Let's go backwards. To play double like that. And what this makes the system now do is, when we calculate 340 divided by 9, it will not remove the digits after the decimal point, because we're no longer working with just integers. It's actually calculating the value, and it will be 7, 7, 7, dot, dot, dot. At some point probably 8, because while we do have decimal points, there's still a limit to the precision. We can get way more precise than integers. We do have all these extra digits after the decimal point, but they're not infinite. We still have only 64 bits in total, and this would be an endless series of 7s. Of course, you can technically create a data type that could accurately store this. I mean, at very least, maybe you store the information that this is 340 divided by 9. But that's a special case, and we're not going to touch that. So floating point numbers are never exact. Unlike with integers, you can't trust them 100%. You always have to assume that they're close to the real number you're targeting, but never exactly the same. Always assume there's a small tolerance in there, especially if you make comparisons. Never trust floating point numbers. Not with exact values. But yeah, so this way we can make this number work. What, however, happens if we mix and match? Let's say I didn't want to use a double for the Fahrenheit. What if this was just an int? The output might have been double. I wanted a precise answer, but the input might have been just an integer. For whatever reason. Well, then things get interesting. Let's back up a bit here. Right now, we are calculating a, an integer, and subtracting 32. Thing is, operations like the minus expect certain data types. It's not like this operation can just work with numbers. We can just say there's a subtraction, there's a minus symbol, so it just takes the numbers. These are also numbers, just not integer numbers. It only works for certain data types, so actually the minus symbol is reused for several different operations, because you can have int on int, or you can have short, or you can have long on long, or you can have double on double, but you cannot have int and double. This does not work. It's not defined. There is no operator that can subtract a double from an int. That doesn't mean this code wouldn't work, that we can't make use of that, but we have to be a bit aware of the differences between data types. That's all there is. So right now, the compiler sees, or the computer sees a, which is an integer, and is the number 32. 32 is an integer number. It's just a simple, straightforward whole number. And so the computer internally assumes this is type integer. It just assigns the data type for us with a default value, 32. And so we have an integer minus integer, which is defined as an operation that it can do. It subtracts 32 from the integer and gets a new result, which is also an integer. So whenever you combine two different numbers with the same data type, the subtraction will create a result with the same data type. That's why earlier, when we divided 5 by 9, the output was cut off because we have 5, which is identified as integer, and 9, which is identified as integer. Division works with data type, same data type, creating the same data type. Integer divided by integer creates integer. We want but more precision now. We especially have b, which is capable of storing decimals. So we have to somehow tell the system that we don't want to work with integers anymore, the default values here. We want to use floating point arithmetic. We wanted to use doubles or floats, which would work too. And one option we have is to actually write out decimal point, 10, for example, 32.0. So I do this, 32.0. This would not be interpreted as an integer anymore by the computer. Instead it would think, oh, this is a floating point number, there's a decimal point. We care about the decimals. And the default it will go for then is double. So this is now integer minus double. I'm not going to write out that .0 because that looks kind of dumb. Instead I'm just going to go with a D for double. Certain data types have a character you can use to identify the number in front as a specific type, because it should not be the default the computer expects. That's usually for integer values you write down, integer constants. You don't want the computer to use integer, you might want to use something else. So a D for double, or an L for long if you want a 64-bit number, for example, or an F for float. Just some examples. And then the rest times 5 divided by 9. So that's the only number I actually need to change. It's one option I can do, and the rest will work on its own. So let's correct the data on top. Double times 5 divided by 9. So priority to the subtraction, which now has to work with an integer on the left and a double on the right. Subtraction isn't defined for integer minus double. Doesn't exist. But the computer is smart. It knows that this integer could be represented as a double and work. We can absolutely store this value, this 100, as a double. We don't lose any information, so the computer is perfectly fine with doing that on its own. So the first thing that happens is it will cast the value we get into the type double. So what actually is happening here is not 100, but 100 as a double. And that's multiplied by 5 divided by 9. Now this will be calculated as double minus double. So we get b equals 68 as a double times 5 divided by 9. These are still integers. So 68 double times 5 divided by 9. Well, another calculation, double times int doesn't work, not defined. We need the same data type on both sides. So the 5 is converted to a double, because we can, without any issues, convert integer to a double. We don't lose anything. So we have actually d times 5d divided by 9. And we can calculate that, and that's 340 double divided by 9, and then we have to change the format of 9 from integer again to double, which the computer does on its own, and then we have lastly the assignment of 37.777, whatever, which is double. I'm just writing this in the end, but since we have a decimal point, the computer would know as well that this is double. And we can assign it. And then we have a 37.777, whatever. So this is nice. What if B was not double? What if we never changed that? What if we only changed that I add the D in here for the calculation, but the assignment should happen in an int? What now? We now have a B, which we want to assign a double to. Well, this would not work. The compiler would complain that you cannot assign a double, a value with decimals, into an integer, a value where the decimals would get removed. It can't do that. Like, it would have to purposefully lose data. And will not do that on its own. You can, however, tell it to do so. You can tell the computer that is fine. You are free to remove that data. Just make sure you cram that number somehow into the variable. And to do that, we use the same operation you've already seen here, or here. Basically this data type, writing that out for the declaration, well, something similar can be done in here. Only instead of telling the computer that this variable we're just creating is supposed to get a certain data type, we tell the computer that this value that it has should be changed to a different data type. And then I have to remove all this and make this a bit bigger again. How that works is we write brackets, and in those brackets we put the data type we want. And because I want to have the whole term converted, I have to add another set of brackets around. And what was that? A minus 32D times 5 divided by 9. Close brackets, like that. And we have this whole thing. Only it's now placed in brackets with an int in front, like that. So these brackets give priority to everything inside. So this statement is still the end result. B equals int 32.777. And now the computer will try to cram this number into the integer format. It will try to turn this 37.777 into an integer by losing all the data. And so what we're left with is just the 32 as an integer. And now the assignment can happen and put it in the table again, in the memory. And we had to add these brackets because this operation here, this casting operation, that's what it's called, has a higher priority than everything else. So if we had not used these numbers, or these brackets here, it would have converted the result of this A minus 32 double, and then would have done the multiplication. So basically at this step, it would have still calculated 68D, but it then would have converted the 68 double into just 68 integer. And then the rest of the calculation would have happened, which still would have gotten us 37, but it's not technically what we actually try to achieve here. But yeah, casting is a special feature that applies to a lot of things. Especially later on when we create our own data types, casting becomes important. there are two types. There's implicit casting. Implicit casting and explicit casting. With an A. Implicit casting is what we had earlier, when the computer was just perfectly fine with turning this A into a decimal, into a double, or the 5 and the 9. There's no issue with turning an integer into a double or a float, because we don't lose any data. Going from 1, 0, 1, or actually let's use decimals, going from a 25 to a 25.1, well, we didn't lose any information. So that's perfectly fine. But going the other way around, 25.2 going to 25, that's not allowed, because here we lose the information after the decimal point, and the computer will not do that on its own. This is not an implicit way. This happens implicitly, implicit casting. This has to be forced. The computer will not do that on its own. We have to tell the computer to do so. It can do it, but we have to allow it by using explicit casting. Implicit, well, it will just do things on its own. If it sees that it's possible, it will just do so and not complain about it. If it's not possible to do so without losing any information, we have to explicitly tell it to cast with this operation. Brackets and then the data type put in front of whatever we want to convert into that type. And that's for now everything about data types. Let's have a look at operations a bit more. So we had some operations which work on numbers. So we had the plus and minus and divide now and multiplication. And we had operations, at least one operation last time, which worked on Booleans. This and. Then we had some special operations like plus plus, or was it minus equals, where we have assignments and mathematical operations all crammed together, which is just a sequence of operations that are mashed together in one operator, quotation marks, quote-unquote operator, that's just easier to write out or quicker to write, and for experienced programmer also very easy to read. Because unlike a program where I have to read a equals a minus 1, I have to at least parse this briefly. For a long variable name, you might have to actually read out a bit so you don't miss any important information. Or if you just say I minus minus, that's very easy to see. Like one variable and just a minus minus, you immediately know what's going on. You not only understand what's happening, you also understand the intention of the programmer that designed it. Because here, this might not be the actual term that was supposed to be here. It might just look like that. Like maybe there are other things added to that. And they're just removed right now. But here it's very clear the program intended to be this, for this to just be decrement. Done. But these are not technically needed, but they are very useful. These are the base operations we should worry about. So let's ignore them for now. That was just shortcuts. Arithmetic operations are pretty much the same as you know them from math. They just apply to numbers. You just have to be aware that each data type can only be operated on its own. These maybe you should talk about. We have also this one and this one. And actually we have these two, which are the same as these, sort of, but they also work on numbers. So these operations down here are purely for Boolean. Only for Boolean values. They don't work on numbers. These operations just work on numbers. Floating point numbers, integer numbers, doesn't matter. And there's some special meaning, especially these ones here. So these basic math, these ones perform Boolean logic, except these just work on a state term in general. These work bitwise. So let's say I have a number. Actually, we should talk about the operations themselves. So and this and should write this out properly. This downward straight line, the pipe symbol, this is an OR, and the exclamation mark is a NOT. This is some simple Boolean logic. True and false. For example, it's false. Stuff like that. Or true or false. That would be true. And the last one, not false, is true. So and an OR operate on two values. The not applies only to one. And this is just basic Boolean logic. I won't go over that. You can read up on its own. There are a couple of Boolean operators, and these are the most common ones, and or not. The fundamental trio. Trio? There's there's a good word for that. Whatever. Let's forget it. Anyway, these operations are and, or, and not for bools. With a twist we'll get to at some point, hopefully. These are general and, or, and not for bitwise operations. So if I have a number, let's take this number. This is not an actual data type, of course, with just 5 bits, but I couldn't use the Boolean operators on this number because this is a number and they work only for bool, true or false. This is a value. I can use these operators though. If I combine, for example, this with an and use another one, 1 1 0 0 0, like this, it will now make a bitwise and on these two numbers. It will just look at each digit individually and match the counterpart. And that would mean that if we go backwards, we have 0 and 0 is false, 0 and 1 is false, 0 and 1 is false, and 0 is false, and 1 and 1 is true. So a single AND between these two would result in this. And the same way I can also make an OR bitwise, so we'll just make the operation apply to the bits again. So we have 0, 1, 1, 1, 1, bitwise OR. And the NOT also applies bitwise, which is this wavy line, this tilde, sometimes I think it's called, I'm not too sure. This will invert the numbers, so we have now 0, 0, 1, 1, 1. So these operations, they do basic Boolean logic, but they do so on numbers. They do also work on Booleans though. You can also combine, at least, well, this, I'm not too sure about this one actually, but these two actually work on numbers, bitwise. You can use, we can have a bool and bool, which is just and, or you can have bool and bool, which is also just an and. The calculation is the exact same for both. Difference is, this one is just straight up evaluate both sides and then combine them with the AND operation. This one is like a smart AND. It's the most common one you will use also. And we'll first check, is this side true? And if not, well, it will just straight to the end. It will not even look at this term. It knows this term is false. Well, then it knows that the whole statement has to be false as well, because this is an AND. There's no need to even look at this. No matter what is written in here, the entire term will end in false. And in the same way, if you write out this or this, maybe, let's write it this way. Here, it will check the A. And if the A is true, it will just go straight to true. And if it's false, then it will check the second one and might decide to go to true. It's going to be smart about it. It's not wasting time on this second term here, on the second operand, if the first one already decided the entire outcome. If you use the single pipe though, it will still check the second one. Even if it's clear that the outcome will be true, it will still check the second one. And in most programs, at least that I write and read regularly, the two symbol combinations are what you constantly are going to use. There are some circumstances where the program flow requires you to still evaluate the second term because it has other effects, and the logic should still check that, but that's rare. But it's important that you know that. Usually you would use these single terms for bitwise operations on numbers, or just on binary numbers, and these double versions on booleans. You can use these single versions on Boolean too, though. It's just a slight difference in how they work. Now, let's write a simple program once more, just to get in the flow again, because we are actually getting to your homework now. See, there is a certain operation that we can do in C#. In our basic CPU, if you go back, we had only the plus, we didn't have the multiplication. So to multiply values, we actually had to write an algorithm. Well, in C# we do have multiplication, because modern CPUs have actually dedicated hardware to multiply. So we can just use that as an operation. What we don't have is exponents. So you might know this little symbol, this little hat, this little triangle. And that's sometimes used to identify exponents. So x, y, that's the same as x to the power of y. Like sometimes you see this to write it out on a computer. This symbol is used in C# as well, but it's not for creating an exponent or marking down an exponent. It's used for another logical operation, the XOR. So like that. We don't have any specific operation that would let us create the square, for example, of a value, or the cube of a value. They don't exist. There are ways to create that in C#. There are existing functions you can tap into, but there is no fundamental operation you can use for that. And your homework will be to create a system that will do, let's say, cubes for now. And to recap, we're just going to recreate the program from last time. A program that can multiply two values. Don't worry, the homework this time is pretty simple actually. This is just to get a bit of a warm-up for you. So we're also gonna stick to integer values, and we are going to ignore any negative values. So the initial program that you're gonna start with It's gonna have an A, which we set to a value. It's 4. Like, this is the warm-up, so my values are just gonna be smaller. 3. And I have an int product, which I'm not going to define yet. Now to create the product between A and B, we're going to use the very simple algorithm I used initially. It's the same one we actually implemented last time at the end of the video. So if you still remember that, well, good for you. I don't, so I have to still create that by hand now. I think the first one was we check if A, no, if we're gonna decrement A and add B. So we have to check if B is 0. So first order of business, we initialize product with the default value. Actually, I'm gonna be lazy. I'm just gonna call it P. With an int P, which doesn't have a value. That's 3, that's 4. So P equals 0. Then if we're gonna actually make the shortcut version. No, we're gonna write this out properly. We're gonna write this out properly, and I'm write it on the right side here. So P equals 0. Then we have to check if B is, that's how I did, right? I have to decrement A, so I have to check A for 0 anyway. That's gonna be put in the loop, so the only individual check we have to do is for B. If, and then we had the brackets. You mind, if was if brackets and curly brackets. One is the condition and one is the code block. If, and the condition was if B is 0 or less. So yeah, forgot that. We had still other operations that said last time that I didn't list. If B is less than 1. For example, this would be if B is 0 or less. You can also write if B is less than or equal to 0. This is also a way to write this. Actually, we don't want to do something when it's 0 or less. We want to do something if it's greater than 0. Greater than 0. That. And then we're gonna open up a bracket here, which doesn't look so pretty, but let's try that again. Better, whatever. And we're writing this out fully, so later on we have to close the bracket down here. But if B is greater than 0, then not B. Not B. Come on. While brackets A is greater than 0. Same condition, but for A. And this time for the loop. Another bracket. While A is greater than 0, we're gonna set P to P plus B. And then we're gonna set A to A minus 1. And then we can close this bracket. And then we can close this bracket. And that's our program. So if we start with this on the left side, everything is set up, declared, and partially initialized. Then the start of our actual program, we start by initializing this at 0. And then as long as B is greater than 0, which, look on our table, it is. Gonna go into this part here, into the inner block. Then we have a loop, which gonna check first if A is greater than 0, which it is. Then we're gonna set B to a value which is calculated by P plus B. 0 plus 3 is 3. We add that to p, so this is now 3. And then we go to a equals a minus 1, which means we subtract 1 from a, and the result is stored in a. So 4 minus 1 is 3, which we store, and it's 3. And then we add, at the end of the loop, we go back up to check this condition again. A greater than 0, which is still true. We add to p, the b, which is 6. We subtract 1 from a, 2. We repeat the loop, which is still true. We add b. We subtract 1. We check the condition, still true. We add to b. We subtract 1, which is 0. We go back to the loop and check the condition, which now is false. A is not greater than 0. So we jump to the end of the loop and reached also the end of our if. And that means we reached the end of our program, and b is indeed 4 times 3, 12. So the program worked. Let's reset this to the beginning. The shorter version let's clean that up here, like that. The shorter version was the shortcuts that I showed you earlier, and here we have just -1 on a, so we can replace this with an a minus minus, and this up here is just adding b to p, b like that. Same statement, just in shorter form, making it quicker to write and easier to read, if you're familiar with the operations at least, because you immediately know what the intention was. We increase p by b. Very straightforward. We decrement a. Very simple, straightforward. And now we actually see another adventure we can do, because keep in mind, minus minus a minus minus, same operation, both decrement a. Just in this case, we decrement a and then return a to use it again. And this one also returns a, but before the decrement. So in both cases, we decrement a, and in both cases, we get the value of a to use in the rest of our operations. Just in the first one, we get the decremented value, and this one we get the value before decrementing it. So in our case, we always check the condition where we need a, and then we decrement it down here. So we can just write this and put that in one line, and we get a minus minus to decrement a, but that happens after we've read out 8 for our operation. So if we write this line, we process this while a minus minus greater than 0. Well, we would first look up a and have a while for greater 0. But then after we look it up, we also have to decrement it again. So this is what would happen here. We still check the for, the initial value, just like before in our old program, but we also decrement it without having to write this line specifically down here. Again, just shortcuts, just to make the program more compact. And since we removed this line, we can also remove the semicolon because we don't need an empty instruction. And because it's only one line, we also can remove the brackets, because compiler will automatically assume that there are curly brackets to indicate the code block if there's only one line. If the brackets are missing, the first instruction is considered to be part of the code block, the second instruction, if there is one, is not. Also, the entire statement, the while, the header basically for the loop, and the code block below are grouped together like one large code block. It's like this code block here and this line belong together. So even though the brackets are gone, this whole thing, these two lines are one code block. And so because we only have one code block, We can also remove these. Because still, compiler will not see any curly brackets, so it will just assume the next instruction is the only instruction for the code block, and it will see the loop, and because the loop is actually this whole thing, it will automatically know that these 2 lines are the entire code block for the if, and we saved ourselves some space and have a fully functional program still. I'm one for one repeating what we did at the end of the last lesson. This just to write it out again in this new format. And this is so you now have a basis to work with when writing your code. See, I want you to cube 2 values. And the first one goes in AC. The second one goes to BC. Write a program. Let's write out homework. AC, BC. Complete the program. AC is A cubed and BC equal to B cubed. By the end of the program, AC and BC should be A and B cubed. That's gonna be your homework. You can use everything you've seen so far to recreate it. You can basically adapt my program from earlier. You have to just pay attention to a few small details, and maybe you can find ways to make this more efficient. But that's basically it. And that's where we're gonna stop for today. Thank you for joining in. Think of your homework. I'll see you next Sunday.